Okay. Hello, everyone. Welcome to today's Quantum Spacetime seminar. We are very happy to have Julio Parra Martinez from CALTECH, who will tell us about causality constraints on corrections to Einstein's gravity. Over to Julio.
Okay, thanks a lot. Thanks for the introduction and for inviting me to give this talk. It's very exciting to also meet some new people, even if virtually. So I'm going to tell you about this paper that came out I guess a month ago, more or less, a bit less, with Simone Kernhout, David Simmons-Duffin, and Yoja Lee, which is Simone's student. And essentially, given these kind of spectacular experiments that we have seen in the last few years, the kind of gravitational experiments that are telling us that we are entering a new era in our understanding of gravity experimentally. I think we like to say that these things are going to test GR, but we really should ask ourselves, what are we going to learn from these experiments? We should kind of get our theory straight and try to answer this question. And one of the motivations of my talk is to convince you that these tests of GR, what they're actually testing is the question, can signals travel faster than light? Okay, so I'll be driving towards this. And we'll see how I will show you this in a technical way, but this is the basic point of my talk. Okay, so this is the outline. First, I will describe the class of modifications of gravity that will be considered. So I will be considering effective theories of gravity. And then we'll try to understand how causality can constrain these theories. And then we can, once we know the constraints from causality that relate to this question of whether signals can travel faster than light, we can see how experiments that kind of test these modifications of GR can tell us something about causality. Okay, so I'll describe kind of the old-fashioned causality bounds that have appeared in the literature in the last 20 years or so, and kind of the modern take on this. And I will show you the bounds that we found on these gravitational effective theories. And then I'll just give a little summary. So let's get started. Let me talk about the class of effective theories of gravity that I'm going to consider. Okay, so we know that at low energies, if you want a theory that describes gravity, Einstein gravity is essentially the only game in town. Okay, and this should be properly understood as an effective theory. We know that the only consistent theory of like a massless spin-2 particle at low energies is Einstein gravity, Einstein-Hilbert, but as an effective theory, it can be modified by a set of high dimension operators, which in 4 dimensions, which will be the focus of my talk, start with a Riemann cubed operator. Okay, there's no such thing as an R² operator in 2 dimensions, which is not a topological like Gauss-Bonnet, or that will have an effect on the class of observables that I'll be talking about. Okay, so the first correction to gravity for me is going to be Riemann cubed, and this EFT is really an expansion in the energies of the gravitons divided by m, where m is kind of the scale of new physics. Okay, so these coefficients, as we'll see in a moment, are going to be suppressed by some scale of kind of new physics that we don't know about. And okay, and these coefficients here can affect many things. Of course, we know that they affect things like black hole entropy, but also things that might be tested at LIGO, like the tidal moments of a black hole. The tidal deformability of a black hole is not the same in Einstein gravity as in a modified theory. Kind of corrections to Newton's potential that are tested in LIGO also depend on these high-dimension operators. And apart from this class of theories, you could ask, oh, what about other things? Can you do a different theory of gravity? And everything one can do is add additional light degrees of freedom. For instance, supergravity, we know that there's a dilaton and a B field, which are also massless bosons, plus a bunch of other stuff. And other theories like FFR theories, theories of torsion, this can be thought of as theories of gravity, where in addition to the graviton, you have a bunch of other scalars or a bunch of other matter fields with very specific interactions. Okay, so I won't be considering those today. I will be considering only gravity. Okay, and the focus of the talk will be these Wilson coefficients right here, and so in principle, these parameterize the space of UV completions of this effective gravitational theory. And So this could be either measured experiment or matched if we know what the theory at high energies look like. For instance, in string theory, we know the values of some of these coefficients. And the kind of questions that we can ask is, if we measure them in units of the higher scale, the scale of new physics, we can ask the question, how large can these coefficients be? Which of course has direct relevance for their measurability at experiments. Also, you might ask, what is this M? What is the scale of new physics? Can we measure them? And there's kind of a naive answer to these questions, which is that we expect that these coefficients are order 1 or certain powers of 4 pi. So this is called naive dimensional analysis. And as far as we knew until recently, this is just a guess. This is just a kind of an argument that this is the size that would be natural for some random theory, and we'll see that we can make a stronger statement than that. And unfortunately, if it's true that these are order 1, then we are unlikely to measure these effects. So I'll come back to that towards the end of the talk. All right, so I'm going to be thinking about the observable that I will use to kind of try to find constraints on these coefficients is the 4 graviton amplitude. And in 4 dimensions, okay, so there's different helicities that one can use, but I will be focusing on the so-called maximal helicity violating sector, which is kind of the 4-point graviton process where you have 2 gravitons with plus helicity and 2 gravitons with minus helicity. And this always has this form that I can show here. So this is some spinor helicity prefactor that essentially encodes the polarizations. And then there's some scalar function of the usual Mandelstam variables S and U, which is like P1 plus P2, P1 plus P3, et cetera, et cetera. Okay, and this function has some symmetry, some crossing symmetry that I'll also talk more about in a bit. All right. So in general, this form is valid both at low energies and at high energies. But at low energies, we can expand this function as a power series in this EFT that I was describing just a second ago. Okay, so this is the form that it takes. So this leading coefficient is just Einstein-Hilbert. So it's 1 over STU. So this is the contribution from the R cubed operator, which here I normalize in some specific way, and its coefficient will be called G3 hat, because in general, there's also a party out component, which doesn't affect this process. And then there's higher derivative corrections, like R to the 4, D squared R to the 4, D to the 4, R to the 4, which will also put bounds on. Okay, so this is going to be the setup. I'm going to work in this EFT of gravity, and I'll be talking about scattering amplitudes. Any questions so far?
So you said let's focus on the MHV sector.
Yeah.
That means 2 pluses and 2 minuses?
Yeah.
Is there anything else for 4-particle scattering?
Yes, there's other helicities, and towards the end of the talk, I will show you bounds also on coefficients that only appear in other helicity configurations. But it's just that technically putting bound on other helicity configurations is a bit more complicated. I can explain at the end why it's a bit harder, but for explaining the main points of our analysis, MHV is enough. Even though in the paper we did more general things.
Okay, and so the others would be like 3 pluses and 1 minus.
Oh, all plus 2 or all minus. So there's three different configurations. Yeah.
Okay, thank you.
So when you're considering the effective field theory, you're essentially ignoring the cosmological constant term that would come out of loop effects, right?
Yes, if you wish, yeah. I'm putting just the cosmological constant to 0. So I'm working in flat space for this analysis. Yeah.
And you're assuming that the loop effect that would affect the R term also is absorbed into the GN.
So let me talk about loops in a second. So actually right now. So there's an extra assumption I'm going to make, which is the following. So I don't want to assume a lot about the UV, but I'm going to assume that there's a large separation, like a large scale separation between M Planck and the scale of new physics. Okay, so we don't need to know much about the UV spectrum. We'll see that the assumptions we're going to make is Lorentz invariance, causality, and unitarity. But we're going to assume this parametric separation, which effectively tells us that we can ignore loops in the EFT, because loops are going to be suppressed by M Planck, and we're going to be looking at much larger effects, which are suppressed by 1 over M, where M is a scale which is much lower than M Planck. One can ask also what happens if one does away with this assumption, and that's one of the questions I'll have at the end.
So effectively, you're trying to constrain theories that are classical at low energies.
Yes, that's right.
Okay, thank you.
But apart from ignoring, apart from assuming that there is a big scale separation, other loop effects could come from having massless, other massless particles.
That's right. That's right. So you could have, but any loop effect where the interactions are gravitational, it will still be suppressed with respect to these things. So you could ask, what about loops in the standard model? But again, I'm talking about the foregravity and amplitude. So M Planck also shows up in their coupling to gravity, so they're also going to be suppressed relative to the effects we'll be talking about. So for instance, this is the case in string theory, that there can be this large separation between the string scale and M Planck, but our results will be valid more generally. And we'll see in a bit that the scale M that I introduced, we can actually really say that it's going to be the higher spin scale. It's not going to be the scale of like massive particles in the standard model or KK modes in some compactification. It's really going to be the higher spin scale. So, another question that I will try to address is, does our consistency impose any constraints on the spectrum?
In general, the cosmological constant is quartically divergent. So it would depend on M Planck to the 4 or whatever your higher scale is. So, so you're assuming that you're absorbing that into the experimental value, right?
Yeah, I'm not going to try to solve the hierarchy problem in this talk. I will just ignore that it exists. And yeah. Okay. So if there are no more questions, let me tell you kind of the old approach for putting bounds on these coefficients using causality. And perhaps the most famous example is this paper by Camaño, Edelstein, and Baldacena and Giordeo. I will be calling CHEMS from now on, and these I will call classical causality bounds, because essentially what they design is an experiment where one has two gravitons or with different helicity scattering of a target that one can take to be other gravitons with fixed helicity, and then they consider the regime where kind of G times the central mass energy squared is very large. So this is kind of the like ultra relativistic scattering, like higher than Planck. So this is kind of a classical regime, but it's still long distances. So they consider only the diagrams, they ignore contacts, and they consider only the diagrams that contribute a long distance. And they had an argument that essentially one can resum the set of diagrams that involve these kind of 3-point couplings. And these exponentiate into some classical, kind of semi-classical phase, which is usually called an iconal phase. And in particular, in 4 dimensions, it takes this very simple form. So these are 2x2 matrix because we can have 2 different helicities for these gravitons. And in my normalization, it's something like this. So B is related to the impact parameter, and S is, again, the center mass energy squared. Okay, so there's some logarithm here because there's kind of an infrared issue in 4 dimensions that we'll see how it appears also in our bounds. So I'll be mostly ignoring this. We can discuss this at the end if you want. This is not there in higher dimensions. But in any case, the point is that this iconal phase, which you can think as kind of the semi-classical on-shell action for this process, if one takes the derivative with respect to the energy of this object, one can calculate the time advance for the process, kind of the classical time advance. And because this has some negative eigenvalues, sorry, usually called the time delay, but we can see because this matrix has some negative eigenvalue, there could be a time advance unless G3 satisfies this kind of bound parametrically. So it has to be much smaller than the minimum impact parameter that we can measure. And because this calculation is done in some EFT context, this is going to be 1/4 powers of M, which in their case was the higher spin scale. Okay, so these are very interesting bounds, but they're not perfect. One of the reasons is because this argument is not really sensitive to quantum interactions. This can only bound G3, but it cannot bound G4, which is the coefficient R to the 4th or other high dimension operators. Okay. Another issue is that these bounds are parametric, because one is working at these kind of large energies in this classical context. So it's not really clear what is the relation between the Higher-Spin scale and this minimum impact parameter that one might be able to measure. Okay, so this is one of the things that we'll try to do better at. Okay, so this is a review of a classic paper. So let me just keep going. And one of the things that I want to make clear that we'll be using to try to got this problem is that Lorentzian EFTs are very different from Euclidean EFTs. And that's why we study scattering as a proof of causality. So let me explain why is that. And the basic idea is that short distance is not the same as, or short distances in a Lorentzian EFT doesn't really mean short distances in space. It really means close to the light cone. Okay, and the regime that probes this, that probes whether things are close to the light cone or they can be kicked out of the light cone, it's forward scattering, or kind of the Regge limit of scattering amplitudes, where we take S to infinity with t fixed. Okay, and this is the regime where we are at risk of being kicked out of the light cone, because particles are exactly forward. So if we have like a time advance or time delay with the wrong sign, we might end up outside of the light cone and then violate causality. This is different from fixed angle scattering, which is S going to infinity with S over T fixed. Fixed is the momentum transfer. And the reason why this is not a problem is because a time advance for a fixed angle scattering is not a problem. One way to see this is that for a fixed angle, no matter how large that is, if it's not too small, then this particle is going to be always in the future of this particle. Another way to see it is an example in this paper by Porter and Giddings, where no one be surprised that if I'm measuring the time advance in some particle that undergoes scattering with some hard sphere, I will see it earlier than I would have seen it if it was traveling in free space. Okay, so fixed angle scattering is not really a proof of causality, but the Regge limit is. And the way we'll use this is as follows. So the notion of causality that we'll be using, rather than the existence of a time advance or time delay, which is kind of a classical notion of causality, it's a bit more subtle. So intuitively, there's several things that relate to causality. One of them is crossing symmetry. So for instance, this is the process, so this is the usual LSD formula for the difference between a particle and its cross version. Okay, so the basic idea is that if these points are outside the light cone, this should vanish and these two should be equal. Of course, this is not exactly true, because the region that probes this configuration, actually this integral doesn't converge, but at least intuitively we can see that crossing symmetry should be closely related to crossing, the fact that we can have propagation of the light cone of a particle as long as the contribution from an ion particle cancels it. And so our assumption of causality will be that 1, we have crossing symmetry, or 2, we have crossing symmetry, and the other well-known notion of causality is that there will be analyticity in the upper half plane of the amplitude, in the upper half plane in S. Okay, and this can also be seen. So I can ignore the second piece if I only consider the future light cone of X, and that's just because this is exponentially suppressed. I should be able to continue the amplitude into the upper half plane. Okay, and we'll see that this notion of causality, and this in the upper half plane and crossing, together with unitarity, will also impose a bound on the Regge growth of the amplitude that will be important for analysis.
Sorry, could you once again say how causality and crossing symmetry are at least intuitively related? I missed it. Please, could you say it again?
Yeah. It's just the question of when is this integral 0. So this integral typically is done in the future light cone, but if it converged outside of the light cone, then it should be 0, because this commutator of the particle 2 and 3, which are situated outside the light cone, is 0. As I said, this is not a technical statement, because this integral doesn't converge, but at least intuitively you could see that when the two operators that kind of create the particle are put outside the light cone, we should get an equality between these two.
Okay, thank you.
Yeah. Okay, so let me give you an example about why these principles put a bound on these Wilson coefficients. So this was done in this paper by Belazzini, Chung, and Remen, and it's based on some kind of other ideas about this in papers that didn't involve gravity. So let's write a sum rule. Let's write the following sum rule, which is I'm going to take this function s at fixed t, and I'm just going to integrate it along like a big arc at infinity, which possibly might cross some cuts where there's some higher UV stuff that I don't know about. But I told you that there will be a bound on the Regge-Grove of the amplitude. So let's assume that we can ignore the contribution of this arc at infinity based on this bound, this high energy bound on the Regge-Grove. And let's just compute this sum rule. Okay, so we can split this into two contributions. The contributions where the EFT is valid, where we can actually trust this EFT expansion of the amplitude, and the rest. Okay, so above m squared, we don't know anything about the precise form of the amplitude, but we can show that it's only the discontinuity across these branch cuts that contribute, which is the imaginary part of the amplitude. And in the forward limit, when I set t equals 0, that is just simply related to the cross section by the optical theorem. Okay, so we can see that at high energies, this is just some average, like at high energies of the cross section. And at low energies, I can explicitly compute this integral, and this will just pick up the residue at s equals 0, which in this particular case is just G4, the coefficient of r to the fourth. Okay, but now because we know that cross sections are positive, because they're a measure of probability of some scattering event, their average will also be positive, and then we can show that this G4 is positive. Okay, so this is an example of a lower bound on some EFT coefficient based on causality. So here we use causality in a few places. First of all, in principle, there's a contribution from the S channel cut and the U channel cut, which I'm relating to each other using crossing, and also by ignoring the arc at infinity, which, as I'll be talking more about in a second, should be also a consequence of causality. Okay, and also I'm using analyticity of the amplitude, of course, to be able to write this integral. So as with the Kemp's bounds, this also has some issues, which is that we can only constrain signs even in S using this kind of exactly forward argument, and also that we can only consider some rules that ignore the contribution from gravity, that are not sensitive to the leading contribution to Einstein-Hilbert, because that would be singular in the t equal to 0 limit, which is where we have some positivity. Okay, so we'll have to do better than this too. Okay, so the general idea is that we wrote some low energy EFT coefficient, some low energy data as a positive sum over UV unknowns. Okay, and this is going to carry over to the bounds that I'm going to write. Okay, so there's another thing, which is this caveat, which is that these bounds that I just showed you relies in particular on this this assumption that is usually made about the Regge-Grove of the amplitude, which is that if you take the amplitude at large s in any direction in the upper half plane, it grows slower than s squared with fixed t. And this is, to my knowledge, is unproven in all generality, except for some cases where it has been shown to follow from a chaos bound plus ADS-CFT plus taking some flat space limit, and it's certainly believed to be true. But we'll see that actually we don't need this for our analysis. Okay. So the question is, can we do better, and what is new with respect to these old ideas?
Julio, one question.
Yeah.
So are you going to use crossing also?
Yes.
Okay.
Yeah. Which is also unproven, but yeah, for massless scattering. Yeah. So yeah. So let's talk about these modern causality bounds, unless there are more questions, and it will be clear what I'll be using. Is there any question about what I just talked about? Okay.
So
these are going
one kind of language question. I mean, so you're calling this causality bounds. I mean, I guess in practice, what you will be using is unitarity, right? So from causality, what you borrow is okay. Maybe it's on this slide here, analyticity.
Yeah.
Okay.
Yeah.
Fine.
So I think we will be using unitarity, but to have some statement about positivity, but I think you will see that some of the new things that I'll be talking about actually stem from crossing rather than from partial wave unitarity, which has been understood for many years, which is why we think of these as causality bounds. But yeah, we can talk later about it, whether this is a good name or not.
Okay, thank you.
And so these are my assumptions. I'm going to assume the low energy spectrum, which is just gravitons. We could include other stuff if we wanted to consider other theories, and that they have an EFT expansion at low energies, the amplitude. We'll assume causality in the form of analyticity of the amplitude, analyticity of the upper half plane and crossing. I will assume that there's Lorentz invariance at all scales below m Planck, so the spectrum is organized by mass and spin. And then I'll also be assuming partial wave unitarity. So partial wave unitarity is if I take the amplitude and I take this imaginary part, I expand it in partial waves. Okay, so in 4 dimensions, this is an expansion in these Wigner-D functions, which are kind of spin analogs of the more familiar, perhaps, Legendre polynomials, with some spectral density, which is positive and also less than 2, and depends on the external helicities of the process, on the spin and on the mass of the every state in the spectrum. And you can think of these essentially as kind of the couplings of higher spin states to the graviton or squared. At least intuitively. And I'll be using this notation, but every time you see this, it's really some spectral density.
Will you be using the less than 2 part or just the greater than 0?
So today I'll just be using greater than 0, and that's what all my bounds will be in ratios of Wilson coefficients. I think it's very interesting to try to use less than 2 also to put absolute bounds on the Wilson coefficients. And I think several groups are thinking about are trying to do that right now, but I won't talk about it. Yeah.
I see. But that changes the problem also, right? Because the way you set it up is perturbative, kind of by construction.
Yes.
So the only relevant is this one. The second part doesn't even play a role, right?
It doesn't play a role, and indeed this is a statement about strong coupling in general. Yeah. So yeah. So that's one of the reasons why
strongly coupled gravity theory. So analyticity properties at 0 would change, and all sorts of things would happen. Right?
Yeah. But we'll see that even just assuming this, we will be able to make some interesting statements about these coefficients.
Yeah. Okay.
In particular about how strongly coupled gravity can be. Okay. So let me keep going. So I'm going to write a bunch of these sum rules. So there's actually a basis of sum rules for this function S, and these are organized in a very specific way, but this is essentially it as far as the MHV amplitude is concerned. This is the basis of sum rules that we'll be considering, and it's organized by K, which we call the Regge spin. And why it's called the Regge spin is because each one of these sum rules converges on a Feynman diagram, which is essentially a spin K exchange. And for different values of K, these will converge or not for this kind of process. And that's why we call this a Regge spin. And all of these vanish based on this assumption about the S squared growth of the amplitude, which I will get rid of in a little bit. And the contour is as follows. So it's just some large arc at infinity, which doesn't really cross the real axis. And the usual argument is that it can be deformed to pick up some discontinuity along some high energy part and then some arc, which will be the low energy part. Okay, so let me talk about each one of these contributions separately. So first, the low energy contribution, which is this arc here, that we can just evaluate explicitly using the EFT expansion, and for us it's very easy because of our weak assumption in the EFT, which means that there's no loop, so it's just some kind of simple residue integral that we need to compute. And for instance, for this sum rule at spin 4 looks like this. So the leading coefficient is this G4. Okay, so if we want G Newton, we need to include B2, which is the spin 2 sum rule. Okay. At high energies, we can evaluate the contribution using the partial wave expansion. Okay, and this is the integral from 0 to infinity of the following. So here I use crossing to relate the contribution from the left cut to some amplitude 2, and I will be using the partial wave expansion to write it as follows. So for this particular process, then we see that there's two contributions with two different dignity functions, because I had kind of S and U channel, and then some function of the momentum exchange and on the masses and the spins of these particles or these states in the UV spectrum. Okay, and this average just means an average over a positive average over masses and spins. Okay. So how can we use this to put a bound? So this is a sum rule, that because I wrote that each one of these contour integrals had to be 0, the low energy part has to be equal to the high energy part. Okay. So if we can find some functional, any operation that we can do, any linear operation that we can do on this high energy contribution, and we find a functional which is positive on every single thing inside of this average, that means acting on these functions of P and of these Wigner-D functions, etc., for all masses and spins, then automatically we get a bound on these low energy coefficients, okay, just by using the sum rule.
Sorry, my internet dropped for a minute. So what happened to your arc at infinity? Are you?
So for the moment, let me assume that I only have spin rules that start at spin 2. So this is going to start at k equals 2. This is equivalent to assuming S squared growth of the amplitude, kind of this classical Regge growth. So the amplitude grows slower than S squared. But I will get rid of that assumption in a bit. Not yet, but I will do that. And I will show you how. So this is not really necessary for this. Okay. Okay, so this should sound familiar. This is very similar to what people do in the conformal bootstrap. Sorry.
Did you use T-channel crossing already?
I use crossing to relate the contribution in the U channel also to an amplitude. Yes.
Right, but then there is this other crossing piece also, right? That usually is what we think about as a non-trivial piece in conform bootstrap, for example. So that piece, have you used that? That is that.
I'm not sure which piece you're talking about. So here there's only contribution. So the low energy EFT amplitude is manifestly crossing symmetric, and the high energy part, there's a contribution from this cut and from this cut. And everything that I need to know is how these two relate to amplitudes. And of course, this one is just the usual discontinuity of the amplitude in the S channel in the physical region. And this one we can relate to an amplitude in the U channel, which is where I've used crossing.
Okay.
Yeah. So yeah, so I will be thinking of this equation as very similar to the crossing equation in the conformal bootstrap, not in a technical sense, but just in the following sense. So in the conformal bootstrap, there's also some consistency condition, which relates certain data about some operators, typically low-lying operators in the spectrum, to a sum over the rest. Okay, so this should remind you of kind of the low energy contribution, the things that we know at low energies, and then the things that we don't know, and the usual strategy is to apply a functional to this relation to put and find something which is positive, say on the right hand side, and then we would find a bound on the data on the left hand side, or try to find a contradiction with this equation. Okay, so yeah, I won't be talking about the technical relation between these things, but the idea is using some functionals which are positive somewhere. Okay, and here we also use crucially unitarity because these coefficients are positive. Okay. So we just need to find things which are positive when acting on the rest of the objects here. And there's a lot of technology from the conformal bootstrap to search for these positive functionals. I'll be showing you some examples in a sec. Okay, so a very simple example which might be familiar for some bootstrap practitioners is a forward limit functional where we just take a bunch of derivatives with respect to P. And then set P equals 0. This should remind you of the usual taking derivatives with respect to some conformal ratio and then setting them equal to the crossing point, something like that. And these are useful because these partial waves, some of them have certain positivity properties. For instance, it's a well-known fact that you take this D00 that showed up earlier. This is nothing less than the familiar Legendre polynomials. And it's well known that all of the derivatives at P equals 0 are positive. Okay, so this is the fact that at x equals 1, the slope of every legitimate polynomial is positive. Okay, and using this, we can prove some bounds. So the simplest one is don't take any derivatives, just evaluate the amplitude at 0. And this is the positivity bound that I showed you a bit earlier that used the forward limit. He phrased in a slightly different way, not in terms of positivity of cross section, but just in terms of positivity of these spectral densities which follow from unitarity. Okay, and okay, so there's an industry about these forward limit functionals. A well-known paper is this EFT Hedron that tries to systematically explore these kind of constraints, at least an approximation to the space of couplings using some linear bounds. But these are not optimal. So I'll be focusing on a different set. And this still has the issue that we cannot deal with these spin to sum rules because gravity diverges in this forward limit. When we set p equals 0, this is the same as t equals 0, and gravity is just divergent. Okay, there's a 1/t singularity. So we need to do better than that. But let me tell you one of the new things that we can learn from.
Sorry, Julio, could you say the last point again? This last point in the slide.
Yeah. So here, if you notice, I use B4, which is the spin 4 sum rule. If instead of this I use B2, then as I will show you in a second, this B2 sum rule has a 1/p squared in it, which stems from the 1/t pole just from graviton exchange in Einstein-Hilbert gravity. So hence, these functionals will not converge when acting on the low energy amplitude because there's poles in P. Okay, so these forward limit functionals can only be used to explore kind of higher dimension operators by themselves, but not to relate them to gravity. Yeah.
Is another way to understand this is it the following that that you expect this sum rule to be valid only in the physical range of momenta, which is when the t is negative. P square is t here, right?
Yes. Yes.
So you are at the boundary of where this is valid. Is this
yes.
How I can understand?
Yes. I mean, if there was no 1/p, then I think we could safely go to the boundary of the physical region, because that is just
then, I mean, you would be. I mean, it's not clear, right? What would happen because the spin to, I mean, the usual Rage boundedness, that a squared Rage boundedness would not be valid.
That's right. That's right. Yeah, but we'll see that we don't need that. So when I get to that, we'll see that.
Okay, sure.
Yeah,
sure.
Yeah, that this is fine. Yeah.
Sorry, and suppose we ask. I mean, we have this left-hand side is equal to the right-hand side, and when you have this gravity exchange, you have a divergence as t goes to 0 on the left-hand side.
Yeah.
So that tells you something about the right-hand side, right? Do you know what it tells you?
Well, yeah, I will give an answer to that question by applying a special kind of function on that. I don't know what it tells you in terms of the divergence, and in particular, I think, for instance, in dimensions greater than 4, it doesn't tell you much, in the sense that we know how to deal with this, and the conclusions are the same. But yeah, I think it's a good question. I don't have a good answer for it.
Just to clarify, of course, one could try to sidestep the issue by looking at things that don't see the divergence.
Yeah.
But the fact that the divergence exists is a physical fact that's telling you something about the high energy spectrum, right?
So yeah, so there is a sum rule that relates that to the high energy spectrum. But on the other hand, we know what this means, which is that there's graviton exchange, so that there's like a massless particle at low energies. So yeah. You could ask, the fact that you have a massless particle or low energies, which is consistently coupled to everything, what does it tell you about high energies? And yeah, I think that's an interesting question. Okay, so let me tell you one of the new ingredients. So this can be merged with this forward limit bound. So there's already been some progress in this direction. And this is one of the things that stem from crossing. And crossing, essentially, one of the things that it tells you is that there's more than one sum rule that measures every coupling. Because you can think of every sum rule as picking up certain monomial in the EFT expansion of the amplitude. And because different monomials are related by crossing, that means that there's different sum rules that pick up same Wilson coefficients. Okay, so this is an example. So this is a spin 5 sum rule. And it also depends on G5, G6, etc., just like the spin 4, which I showed you back here. Okay, so this depended on G4, G3, G5, etc., etc. Okay.
Sorry.
Yeah.
You say this comes from crossing, but of course that's just automatic when you write it as an EFT, right?
Yes, because the low energy EFT amplitude is automatically crossing symmetric. Yeah.
Right. So from your formalism, it's just automatic. Yes.
Yeah. But the important point is that crossing at low energies in the EFT, which seems a vacuous or kind of trivial statement, actually imposes constraints on the high energy spectrum. And this is because there's more than one sum rule that measures every coupling. We can actually construct linear combinations of the sum rules that vanish identically on the low energy contribution, that they only have a high energy contribution. And this is purely a constraint on the high energy spectrum. Okay, so this is an example. So this is an example where we combine some like spin 4, spin 5 higher, such that we cancel all of the contributions in the EFT. And so let's see. So what is this kind of constraint? So this is some function of the spin and the mass of the high energy states. All of these things are positive. There's only, okay, so this, I didn't tell you, but these things, because of some angular momentum selection rule, only start at spin 4. So this is just the idea that, we have spin 2 particles, spin 2 massless particles, and we can, in a certain holistic configuration, they can only decay into something that has spin 4. So the only term in this whole sum, which is negative, is the spin 4 contribution. Okay, so this already tells you that no matter what UV theory looks like, there has to be a spin 4 state in the spectrum. Okay. And also it tells you that the heavy states, the very high spin and very heavy states, they must couple weakly. They cannot couple too strongly, because at most they cannot add to the contribution of the spin 4. Okay, for this to be satisfied, for this to add up to 0. Okay, so I remind you that here 0 is the low energy contribution, which in this case is vanishing. Okay, so actually these are very useful, and they can use to put bounds. And
sorry,
this is
the S channel T channel crossing or the S channel U channel crossing?
So most of the time I'm using SU crossing. Yeah.
Okay. This also uses the same.
But at low energies, it uses like full crossing, which, I mean, in this case, it's only SU because I'm looking at the MHV amplitude. But if you want to consider the full set of helicities, then at low energy you can see that it's fully crossing symmetric because it's graviton scattering. Yeah.
So let me ask what is probably a very stupid question. You got a constraint that came from the fact that your EFT expansion automatically implemented crossing.
Yeah.
And very naively, you might, at least I might have expected that this would tell you that the high energy contribution is also crossing invariant. Mm-hmm. Somehow telling you more. Right? Do you understand why?
Why?
I'm sorry, the question is so vague. Just if you had
no. I think it's just telling you. Yeah. So in terms of the partial wave expansion, actually, it's pretty hard to see what crossing means in the energy spectrum, right? Because when we do a partial wave expansion, we are just choosing some channel, and it's an expansion which is just valid in the physical region of that channel. So maybe this is the statement of crossing at high energies, but phrased in terms of quantities that appear in the partial wave expansion of the amplitude.
Okay, so one could just try to work out the kinematics of crossing in partial wave, right? Mm-hmm. And you say possibly you get this equation out of that kinematics?
Yeah, I haven't tried that. So one could try to relate partial waves in one channel to partial waves in another channel, and then impose crossing symmetry of the full amplitude, and one might get kind of a basis for these relations. But I haven't tried. Yeah, maybe there's more. I don't know. Yeah.
Okay. Thank you.
If there's more, I don't know what it is, which was your original question. Yeah. Okay, so people have used the fact that there's this additional ingredient, this thing that averages to 0, this extra information about the spectrum, to put some bounds on these coefficients. Okay, so this is in a paper by Zvi Bern, Dimitrios Kosmopoulos, and Sasha Gibrov, and this is the result, for instance, of these two coefficients are what I call G6 and G6 prime. So they're coefficients of D to the 4, R to the 4. And the bound that they put is that the ratio cannot be bigger than 6 or smaller than -8 point something. Okay. But if you look at examples that we have about theories that can be like putative UV completion, some examples of things that could generate these EFT coefficients, then for instance, the string theories, or integrating out a loop of massive particles of different spin, we can see that actually the known theories populate as a much smaller region than what these bounds give you. Okay. And so we see that these are kind of far from the theory island. So all of the things I'm talking about are linear in the amplitude. So you could take any linear combination of these theories, of the amplitudes of these theories, and they will give like a proper S matrix. And so one could think of what is the island that is spanned by these theories, and this is far from it. Okay. And also, as I told you, they only use higher spin sum rules. They cannot use spin 2, so these are always kind of homogeneous ratios of higher derivative operators, but they don't talk to G Newton. Okay, so this we also try to do better. And the main thing that will allow us to do better is use a different class of functionals, which were introduced in this paper, which are called impact parameter functionals. And so the basic observation, again, is that this crossing symmetry, these null constraints, they cannot only be used to find constraints on the UV spectrum, but they can also be used to improve sum rules. And by improve, I mean I can find linear combinations that actually truncate in the EFT expansion, which are sensitive only to a finite number of Wilson coefficients in the EFT. Okay. And that means that we can actually take a functional that integrates all the way up to the cutoff. Okay, so we can push the EFT to the limit because we can write a sum rule which is controlled within the EFT all the way up to the cutoff. Okay, and the class of functionals we'll use roughly is some polynomial in this P, in this momentum transfer. Okay. And
so this is the question, I guess, that's valid for this previous analysis also, I guess. And I should know this, but this integral 0 to m dp, this goes into values of t that are greater than 0, right?
That are greater than, yeah. So p is minus t. Sorry, p squared is minus t. So actually, this is fully within the physical region.
Nice. Okay, thank you.
Yeah, I think, yeah, I should have written that equation, but yeah, t equals minus p squared. Yeah. Okay, so the basic intuition for this wave function is that it's some distribution of the momentum transfer such that the wave function is localized at small impact parameters. So one way to see this is by study kind of the contribution on the partial waves at large J and M, and one can show that this is basically this integral of some Bessel function, which is the transverse Fourier transform of the wave function. Okay, so intuitively you can think of this kind of give you a sorry about that, giving you a distribution in the transverse space, and it's localized because we're integrating P from 0 to M. It's localized at small impact parameters. So actually, on impact parameters which are of the order of the cutoff. Okay, and that's because it has compact support in P space. Okay, so because we are only integrating from 0 to M, this means that this has to decay fast when B is large. And also positivity is a transparent statement in impact parameter space, which is just the fact that this wave function is positive. Okay. So in practice, what we do is we impose positivity in the scaling limit, also in large J with M fixed and vice versa. We impose positivity for the lowest values of M and J up to some cutoff. And that way we can try to find functionals which are positive everywhere. So this has big advantages. One is that at least in D greater than 4, the forward limit issue is resolved because we can find functionals that converge and are sensitive to gravity. Okay. In D equals 4, there's still an higher divergence, which is the origin of this log in the chems bound, and we will still have that in our bounds. Okay. So for us, we would just regulate with some P mean, and this means that we can only impose positivity up to a certain impact parameter, but as long as that impact parameter is very large, we can still have consistent positive functionals. Okay, and then the other thing that this these forward limit functionals allow you to do is actually to prove that the amplitude when integrated against this, and I wrote it here as a function of b, which is not really, but at least intuitively, one can prove that the amplitude is bounded by some constant times s. Okay. So if you want to hear the details about this, I can tell you at the end of the talk. But here I want to move on to the results, but we can have a discussion about this. And basically what this means is that, because again, this is some finite integral over some compact support, this object still has the usual analyticity properties and crossing symmetry, et cetera, and then we can derive the dispersion relations directly for this object. Okay, so this is some linear operation which I can commute with this contour integral that I had, and everything I've told you actually, because of this bound, it's true, and it doesn't need this S-squared growth. In fact, we don't even use this. We just use this that this grows smaller than S-squared, which is much weaker than what we can actually prove. Okay. So as I said, we don't need this assumption, and I can tell you the details about the proof at the end.
Sorry, just 1 minute, please. So M psi was this sort of smear impact parameter kind of S matrix.
Yes.
And at least intuitively, I think of something at a fixed value of impact parameter as being more or less the amplitude at a fixed value of J.
Yeah.
So this is an amplitude that has some support in some range of J's.
Yes.
Or more, I suppose more precisely, large J's scaling 1 over square root S or something like that, right?
Yes.
Okay, I see.
Yes.
Now, suppose I
just a comment. So the usual trouble with just going to impact parameter space is that one cannot control the contributions from large spin, right? And here they're completely under control because I know what my cutoff is. So I know which range of spins exactly.
Okay. Sorry. So could I ask, suppose I just looked at this is probably very stupid, but let me just make sure. If I look at an impact parameter, just the scattering amplitude at just some fixed J, well, does that have good analyticity properties? Well,
that is a partial wave amplitude, right?
Yes.
And it has good analyticity properties in the S channel cut, but not elsewhere.
For instance, at negative S, it does some funny stuff, right?
Exactly. Yeah.
So exactly. The smearing that you guys do gets rid of that bad stuff?
Yes.
I see.
Yeah. And I can tell you more later, but the basic idea is this doesn't spoil any of the analyticity properties that we know, neither crossing, because it's some finite integral over like a finite range of values of t, as opposed to the usual going to impact parameter space, which is something that is at fixed S, but that includes a large range of spins, or just the usual partial wave expansion, which is something much more violent, which is take the amplitude at fixed angle and do some integral, which you cannot control what is happening. So here it's important that we take the amplitude at fixed S and then do some finite integral over t, which means that all our properties carry over.
So it's sort of almost going to impact parameter space, but then smearing that out of it, right?
Yes, and making sure that there's only contributions from small enough impact parameters. So if you wish, the compact support is telling you go to impact parameter space, but with a wave function that tells you that only small impact parameters contribute.
Thank you.
Sorry, Julio, I mean, most of this juice is coming from t equal to 0 piece only, right? I mean, of this range, or
so the t, so the t equals to 0 piece is precisely the large impact parameter piece, which is suppressed here.
Okay.
So this wave function will be mostly localized around t equals n.
I see.
Yeah.
And this bound of M psi over S is basically, it has a feeling of you're using this non-perturbative unitarity kind of statement, right? Partial waves being bounded by 2. It has that feel.
Yes.
Is that where it comes from?
Yes. So the proof is essentially once you've controlled the contribution from large spins, you can use partial wave unitarity to bound the amplitude in a trivial way. Yeah.
I see. But that is interesting because that is a different physics, right? Which you had not touched. so far.
Well,
But
I
we are
think this
using-
statement goes beyond my assumptions in the sense that this doesn't rely on any of the assumptions of weak coupling, or this is just a more general statement that we are using.
Yeah.
Yeah.
Thanks.
Sure. Okay, so finally, I'm ready to show you some results. So let's get on to this. And before I do that, I'll tell you something, which is why is gravity special compared to other theories? Because everything I said so far, I was using the example of gravity, but one could do this in some other theories. So what's very special about gravity is a phenomenon called usually superconvergence, which is the idea that we know something in addition. We know something more about the amplitude, and what we know is that it's proportional to this spinor helicity prefactor. Okay, so here is some example, and this contributes to the high energy growth of the amplitude. Okay, so if you have some bound on the energy growth of the amplitude, then a lot of that is actually accounted already by this prefactor, which we know at all energies. Okay. Just based on essentially Lorentz invariant little group properties of the amplitude. And this means that actually this function that parameterize our EFT or our amplitude in general grows much slower than you expected. Okay. And in particular means that this function actually satisfies anti-subtractive dispersion relations. Dispersion relations will actually multiply instead of divide by some prefactor, and it still converges at high energies. Okay. And because I'm not dividing by something, the contact interactions just don't contribute to these sum rules. Because typically a contact interaction contributes because you have some polynomial in S and T, and then you have 1 over S, so there's some residue that you pick up. Okay, but if here you're multiplying, there's no way that a contact interaction is going to contribute. So as an example, this sum rule in particular just receives contributions from gravity and R cubed. Okay. So this is extremely powerful, and let me tell you why.
Sorry, Julio. Sorry, just because that the last slide was, I mean, which that seemed important, the previous one, because you're getting rid of that. I mean, just the previous before that also, before this slide. Yeah. Yes. Here m psi divided by s is less than equal to 1. So does this, for example, rule out even Einstein gravity or what? Because let's say just you take s square by t kind of amplitude, let's say just in pure Einstein gravity, right? And then because you are going to this impact parameter basis, you would just do, you would integrate over t. So, but s square dependence will be s square dependence, right? Yeah. And then this will go m divided by psi, m psi divided by s would go like s. Yeah. There was an s square dependence. So that this does not obey that. Yes. So I was just worried about that. How does that work there? Just in the case of
this just tells you that just gravity by itself cannot make sense at arbitrarily high energies.
Does not make sense. Is that what you're saying?
Yeah.
Is that what you're telling? Is that what this is saying? But because another thing is that it's classical, right? I mean, that the classical, you cannot quite argue for this inequality for classical theory, because maybe there are quantum corrections which would end up.
No, but our argument for this has nothing to do with classical and using a tree-level approximation or anything like that. The argument is more general.
In 37, okay, then history 40, geography 38. They got those 2 marks, I think.
I think that this you could try to use it to rule out gravity by choosing an appropriate wave function. I will do something which is not that, but it's going to be similar in spirit.
Yeah, no, I didn't count technical drawing in this.
Okay, excellent.
Because they count only the first 5.
Hi, Julio, sorry. A quick question. Suppose we take gravity iconalized.
Yeah.
That is believed to apply, at least in some situations, to very high energies, right?
Yes. That saturates this P2 sum rule. Yeah.
Okay, fine. Because you're in 4 dimensions. The iconal growth is dimension dependent and has a...
Yeah.
Okay, fine. Thank you.
Yeah. Yeah, in 4 dimensions that saturates the sum rule, but then there's like some infrared issues. So 4 dimensions is special, but yeah, it's true that in 4 dimensions, this Regge limit of graviton scattering is unitarized by just gravity itself, by the diagonal approximation. But this is a special statement, yeah.
Thank you.
Yeah. Okay, so are there more questions? I know this is an important point.
So does this go towards answering my problem, my question also, that the way this would work is that you iconalize?
Yeah, I think so. I think that he's saying that.
Yeah, in 4 dimensions, yes, in 4 dimensions. So the answer to your question was gravity does satisfy this, but not in higher dimensions or in more generality. Yeah.
Okay.
Yeah.
Thanks.
Just to say, Julio, I'm really sorry I have to leave for an administrative meeting, but it's like a fantastic talk. I'll watch the recording. Sorry for this.
Thanks a lot. No worries. Yeah. Okay, so let me show you why this superconvergence is amazing. And it's because I told you that there's a sum rule that the low energies only receives contributions from gravity and r cubed. Okay. So let me try to find a functional, one of these wave functions, that gives me 1 or some constant when it acts on the gravity contribution, 1 over p squared, and it vanishes on g cubed. And that is also positive on the Heine spectrum as usual. This implies the following kind of sum rule. This implies a sum rule that tells you that the sum over all 3-point coefficients to my UV stuff, the sum over all like heavy spectral densities, times a positive number can amount at most to G. Okay? So this proves several things. First, it's a mathematical proof that gravity is attractive, but maybe that's not so surprising. But perhaps more interestingly, it's telling you that all this UV stuff, it has to couple weakly, okay? Because at most it can couple, like this is a positive sum over things which are squared. So all this UV spectrum, all these spectral densities, they're bounded by G. Okay. This is very different, for instance, for a theory of Golson bosons, right? In theory of Golson bosons, we know that there's several options. We have things like pions, which are actually strongly coupled to other resonances, and then we have things like the longitudinal mode of the Higgs, which is actually weakly coupled. So there's some weak coupling, which is the electroweak coupling that suppresses these interactions. But there's also the option of having strong coupling. In gravity, we only have one option, which is weak coupling. Okay.
So M is what G was. Is it Newton's constant?
Yeah, G is Newton's constant. Yeah.
Okay.
Maybe I called it Gn somewhere else. No, yeah, it's Newton's constant. Yeah. So if okay, so maybe the precise statement is if gravity is weakly coupled to low energies, then it's weakly coupled at all scales below m. Okay, and by the way, this guarantees that there's going to be bounds on the couplings that look like this. So in units of the UV cutoff, that they're going to be bounded by G. All right, because I already know that at most they can give me G. So here's an example. So this is of one of the functionals that we use. So this is a functional. It's not optimal, but it's some simple example that measures G3, that measures the coupling of R cubed. Okay. So this is I integrate with some IR cutoff, the B2 and the B3 sum rules with some polynomial in V. Okay, and this is what it looks like when I plot it in M and B space. So B is just J over M, essentially. And as I promised, this thing grows for large values of M and for large values of G, and it's smaller for small values. So this thing is mostly localized at large impact parameters. Okay, and it's positive. So here this is some contour plot that tells you the value, and it's positive everywhere. And one can see that it's actually positive in all of these directions. Okay, and by applying this to these sum rules, we can get the following bound, which is not optimal, but it's a bound that bounds G3 in terms of G. So here I remind you that I normalize my G3 coefficient by G, so it's homogeneous in G, but basically this is a bound which is precisely as one would expect from chems, but with a sharp numerical coefficient. Okay, instead of G3 has to be much, much smaller than 1 over m to the 4th times something that I don't know. Here, this is a sharp bound. Okay, any questions about that? So let me show you something a bit better. So this is kind of the contour, the exclusion plot that we can draw. So here is the G3 divided by G Newton. This is G4, which is the R to the 4th coefficient. And this is the region which is allowed. Okay, so this is a bound. This tangent here to the origin is a bound that one can prove using simpler kind of forward limit considerations and higher spin sum rules. But in general, what we find is that G3 squared, okay, obviously it's positive, but it cannot be too large, and G4 also cannot be too large. Okay, so here there's two pieces. I will explain what they mean in a second. But the basic idea is that, how long do I have left, by the way?
Yeah, you can take, how much time do you need?
Maybe 10 minutes.
Yeah, sure.
Okay, great. Okay, so anyway, this is the bound. Here we are including also the possibility of having light matter, light state with spin less than 2. I will explain to you in a second how I do that. But we can see that in either case, the coefficients are essentially order 1 or some power of 4 pi. Okay, so they are small. And this has many implications. If you make extra assumptions, for instance, if you assume that the UV spectrum is weakly coupled, as in string theory, it tells you that you cannot have too many particles that give contributions to these Wilson coefficients for a given value of the weak coupling. Okay. So why we have two kinds of bounds is because we actually allow contributions from things that have spin less than 2 in the EFT. And the idea is to probe things like, what if I have some compactification? And what if I want to kind of mod out by the contribution from these KK modes in my bounds, so to make sure that I'm actually bounding things in terms of the higher spin scale, which is like genuinely gravitational. So this weak coupling assumption already tells you that the KK modes shouldn't really affect the bounds qualitatively, because there's no like 2 graviton 1 KK mode coupling in kind of usual product compactifications because of orthogonality of wave functions in the compact space. Okay, so these would only enter through loops, which are kind of removed by our assumption. But this we can test explicitly just by calculating the low energy amplitudes of gravitons with this KK mode exchange, or with this like spin less than 2 matter exchange, which in fact for gravitons, again, because of angular momentum selection rules, that can only be spin 0 or spin 2. So these are the contributions. And what we find is that the bounds are qualitatively unchanged. So this is it's a bit stronger if you don't assume that you have light matter, but even if you assume that you have light matter, we still have the same qualitative result. Okay, so what is the relation to the Kemp's argument? The relation to the Kemp's argument is we can actually consider a matrix of these sum rules. And we can find that if one considers this kind of matrix of sum rules, roughly this is the same as some particular combination of our sum rules. Okay, and if one evaluates the low energy contribution to this, one finds precisely the Kemp's phase, which in their argument was used as a semi-classical phase of some semi-classical on-shell action that was argued that built up some classical time advance that was in violation of causality. But for us, we don't need to consider that kind of long distance, very high energy regime. We just need to compare this low energy contribution to the high energy contribution, which we can organize in, well, first of all, it's localized for impact parameters, which are related to the spin, if we go to impact parameter space. And second, we can manifestly write it as a positive linear combination of this high energy kind of spectral densities or couplings. Okay, so here there's a type of, this should be B instead of beta. This is just some complex number that parameterizes the impact parameter. Okay, and so the difference is that instead of considering GS much greater than 1, which was this kind of classical long distance high energy scattering that was considered in Kemp's, we really consider GS much less than 1. And in particular, because we're integrating against these impact parameter wave functions, we have control over precisely the range of P, and hence precisely the range of B's that we have, which is why we have a sharp bound rather than a parametric bound. Okay, but this shows you that essentially the Kemp's bounds are subsumed by our sum rules. That they're just part of the sum rules. Okay. So this is some other example where again we can compare the forward limit results with our bounds, which are these regions here. For instance, this is for a party-odd Wilson coefficient, party-odd d-squared fourth operator. These lines here, what they represent is again results in different theories. Okay, because we have this logarithm, we cannot compare directly to the values of these Wilson coefficients in these theories or in some string theory, but the ratio is well defined, which is why we have some line here in this plot. So the ratio of these two Wilson coefficients is we can compare to some UV completion, and then we see that roughly they span the region that we have considered. Of course, this needs to be cut off here, but we can see that it's pretty close to saturating kind of the examples that we know, except that there's nothing at the boundary, like in the usual kind of the famous plots for the conformal bootstrap. Here, the theories that we have seem to lie still far from the boundary. Okay. What about these homogeneous bounds on the couplings? Is the ones that I showed you a bit earlier. So we can do a bit better. So this line here, and if I zoom in to the corner, this line here. So this is the ratios of G6 and G6 prime, which I showed you that was bounded by Sasha and friends. And indeed, their bounds asymptotically are the best that one can do. But we can see that by considering these inhomogeneous ratios, we can actually narrow down the region much more. And in particular, our bounds asymptotically converge to this kind of theory island. Not exactly only in the limit where one takes this, but for instance, we can prove that this guy has to be positive, which brings it down here pretty sharply. Okay, so we can see that including a spin 2 allows you to do much better than ignoring spin 2. Okay, so this is just very quickly, what are the consequences of this experimentally? I told you that the Wilson coefficients are order 1 in terms of this higher spin scale, and there's pretty strong bounds on this higher spin scale from colliders. So for instance, we would find if there was some effect that violates, like that deviates from GR for some black hole measure, say by LIGO. So these 10 solar masses, this is order like 30 kilometers. One could have said, okay, this is accounted by an operator, which is kind of 10 to the minus 20, the deviation from GR suppressed by this scale, which is related to the scale where we saw the effect. And our bounds imply that then there should be some light higher spin state with the following mass. Okay. Okay, so this depends a little bit on the model, but essentially collider bounds rule out these sort of things. So this is telling you that if we saw a deviation from GR, then there should be a super light higher spin state somewhere to be found. Okay, and another way of saying this is that if the corrections of GR are always small, unless the higher spin scale is very low, or unless our understanding of causality is lacking. So all of these things that I told you relied heavily on crossing, and some of these things that we think are consequences of causality. If any of these things is not true, then one might be able to avoid these bounds. But another way to say this is that what the experiments are actually going to test is our understanding of causality, which, as I promised you at the beginning, I will try to convince you that the experiments are actually testing causality. This is a sense in which they're testing causality. They're gonna tell us if there's a deviation for GR. They're gonna tell us either you should look for a light higher spin particle, or we got something wrong. Okay, so I will finish with some conclusions. Yeah, let me just say it very quickly. We have leveraged kind of causality and ideas from amplitudes and the bootstrap in a new way that essentially allows us to prove the expectations from the measure analysis on these Wilson coefficients in gravitational EFTs. Unfortunately, this means that probably we won't test these corrections at GR anytime soon, or if we do, it will be very shocking, because that will mean that we don't really understand causality, or at least some of these basic principles that we believe to be true in amplitudes. There's still some wiggle room. I just consider gravity. One can try to add other matter, other kind of theories like this f of r, which we cannot really probe because our bounds are only sensitive to things that couple at least like gravity with as many derivatives as gravity. But there's kind of some big questions that one can ask, like how much can iron consistency tell us about the UV spectrum? How much are the islands that are going to shrink? Like these bounds I showed you essentially converge. So if we want to push them even narrower, then we need to find other principles that will constrain these EFT coefficients. If we keep shrinking this space, this kind of relates to some of these swampland questions that people have asked. How big is really the swampland? Can we narrow down the swampland using only infrared consistency conditions? And if so, is it really empty? If pure infrared considerations can narrow down the space of couplings. If you believe that the answer is no, then this means that we are not going to narrow down string theory using these principles. If you believe the answer is yes, then perhaps with some additional assumptions, one could try to narrow down these Wilson coefficients to the values in string theory. Okay, and this is kind of a list of things that one could go on and do next, which I think are very interesting. One can try to bound these couplings to matter, to consider loops, which is something that we are looking at. How do they consider the bound? How they modify the bounds? What about higher dimensions? Do these qualitative lessons hold in higher dimensions still? Can we relax the weak coupling assumption? Can we ask about some of the sum rules in a strongly coupled theory? A toy model for this would be pions in the Carré Lagrangian. And also, can we remove these IR logs in 4 dimensions? Can we apply these to other EFTs like standard model EFT starting at dimension 8 operators? So I think all of these are very interesting questions that we can try to address now with the sort of techniques that I told you about. And I think with that, I will finish it. Thanks.
Let's thank Julio for a very nice talk. Yeah, questions?
So, sorry, Julio, just asking a similar question again. But did you use ST channel crossing anywhere in the later part of the talk?
I use it implicitly almost everywhere. For instance, I use it at low energies. It's obvious. At high energies, I use it to write the high energy contribution in a way that I know, basically. So the example was, let me try to go back. Actually, even when I write something like this here, I'm already using crossing, like SU crossing.
Yeah, I'm talking about ST crossing.
ST crossing. No.
Yes, thank you. Okay.
Yeah, which is why we can use these impact parameter functionals.
Right.
Yeah.
Right.
Yeah.
Yes, thank you.
Sorry, I misunderstood. Yeah.
Okay, if there are no further questions, then let's thank the speaker again.
Thank you, Julio. Very nice talk. Wonderful. Thanks a lot.
Thanks a lot. Okay.
Yeah, nice to meet everyone. Yeah.
Yeah. Hope to
And
see
thanks
you.
for the many interesting questions. Yeah. Yeah.
Bye.
Bye.
Okay. Bye, everyone.
Bye.